Iron is a component of several enzymes, including myoglobin and hemoglobin, and is essential for hemopoiesis. The daily iron requirement is around 10 milligrams for men and 15 milligrams for women of reproductive age. It is absorbed in duodenum and upper jejunum. Iron loss is slight, as seen by the peeling of skin cells and menstruation in women. Unlike other ions, such as calcium or magnesium, iron excretion is not regulated. Therefore, iron stores depend almost entirely on absorption from food. Iron is absorbed from food in the form of heme and non-heme iron. Non-heme iron is found in two forms: divalent ferrous or trivalent ferric iron. Vitamin C can increase the absorption of non-heme iron by reducing trivalent iron to the soluble divalent form, especially in the stomach's acidic environment. The enzyme duodenal cytochrome reductase is found in duodenal enterocytes. It reduces the insoluble trivalent ion to the soluble divalent ion, which is then absorbed into the cytoplasm of the enterocytes via DMT transporter, which stands for divalent ion metal transporter, by symport with the hydrogen ion. With our dietary habits, the largest source of iron is heme iron. The porphyric nucleus also absorbs it via the heme transporter. Heme oxidase within the enterocytes then release the divalent iron into the pool of free divalent iron within the enterocytes. The divalent ions are toxic to the cell. In the presence of hydrogen peroxidase, a highly reactive hydroxyl radical is formed due to the so-called Fenton reaction. So the level of free divalent iron must be kept at minimum concentration in the cell that will not damage the cell. Divalent iron concentration therefore inhibits iron traces from the duodenal lumen into the cells, and the divalent iron is converted to the ferritin, where it is stored in the less reactive trivalent form. One molecule of ferritin can contain up to 45,000 molecules of trivalent iron. The primary function of duodenal enterocytes is not to store iron. Hepatocytes in the liver primarily perform this function. The main function of duodenal enterocytes is to transport it into the blood, through which iron is further transported to cells throughout the body. Iron is transported from the enterocytes to the interstitial space only in its divalent form from the cytoplasmatic iron reserve via a transmembrane carrier ferroportin located on the basolateral part of the plasma membrane. After the passage of divalent ferrous iron by ferroportin from the enterocytes into the subepithelial space, the ferrous iron is oxidized to trivalent ferric iron by transmembrane peroxidase Hephaestin. Hephaestin is highly homologous to the enzyme ceruloplasmin, which plays a crucial role in copper metabolism. Serum ceruloplasmin binds copper. After iron is converted by Hephaestin to its trivalent form, It's bound to the central iron transport glycoprotein, transferrin. Transferrin is a complex of the beta-globulin molecule, apotransferrin, synthesized in the liver that can bind two atoms of trivalent iron. Transferrin carries iron into cells. For transferrin to transport ions to their destination, the cell must have the appropriate receptor on its surface, the transferrin receptor. The transferrin receptor is abundantly expressed of all body cells, but most abundantly on erythroblasts, which require a high iron intake for their development. Each cell locally regulates its iron content. The ready supply of divalent iron feedback blocks iron uptake via non-heme and heme iron carriers. A rise in ferrous iron levels increases iron deposition into ferritin. The iron-iron pool also influences ferroportin translation. As iron levels fall, ferroportin production decreases, whereas elevated levels increase ferroportin production. The primary function of duodenal enterocytes is not to store iron, which is mainly performed by hepatocytes in the liver, but to transport it into the blood, where it is further transported to the cells throughout the body. Therefore, the duodenal cell is primary gateway for iron into the body. Hepcidin, an essential regulatory proteins in the metabolism of iron, synthesized in hepatocytes, regulates the number of ferroportin carriers in the membrane. The mechanism of action of hepcidin is to reduce the concentration of ferroportin exporters. It binds to ferroportin, which is internalized, plunged into the cells, and reduces the number of transporters in the membrane. Thus, the iron flux from the cells to the plasma is effectively reduced, where transferrin saturation decreases. Decreases in hepcidin thus reduces iron absorption from the enterocytes. Iron remains in the enterocyte cell and doesn't enter the blood. Recall that enterocytes are renewed approximately every 7 days, and the sloughed off enterocytes and their iron stores pass out the body through the stool. Hepcidin is a hormone synthesized in the liver. Its level decreases when iron decreases and increases when iron rises. Regulation of iron intake must ensure increased absorption when iron deficiency occurs. Since the regulation is not an iron output but only an iron intake, it must also ensure that the body doesn't become iron overloaded by inadequate absorption. Hepcidin prevents iron overload by blocking ferroportin. Hepcidin is a hormone that controls iron metabolism in the body. It's transported by the blood to the target tissues. In enterocytes, hepatocytes, and macrophages, it blocks the export of iron from the cells. In other words, it keeps iron in the cell. Hepcidin synthesis is dramatically stimulated in inflammation or infection by mechanisms independent of the current iron concentration or erythropoietic activity. Hepcidin regulation is phylogenetically ancient defense reaction of iron retention when the organism is attacked by an enemy such as microbes. The purpose of this evolutionary conserved response is to prevent microbes from accessing iron, which could be used as a growth factor. Increased hepcidin synthesis in this pathological condition is mediated primarily by interleukin-6, IL-6. It appears that interleukin-6 may also directly affect ferroportin translation. An increase in interleukin-6 levels leads to decrease in ferroportin translation and a decrease in the amount of this carrier on the basal side of the duodenal cells. Experimentally, it is possible to induce an inflammatory response by injecting oligosaccharide, a bacteria wall component. Confucius wrote more than 4,000 years ago, "When I hear, I forget. When I see, I remember. But when I do, I understand." To help you understand how the mechanism of iron regulation works, we have created a simulation model with a background of interactive animated images. The model is based on experimental data on mice. The values of each variable are therefore relative. 1 is norm, greater than 1 is an increase, and below 1 is decrease. In our simulation, increases or decreases in transporters will be represented by narrowing or expanding the respective transporter icons. Please now walk through the following questions separately using the simulation games with the model.